Okay. So this is where the fun comes, right? And this is where, at various times, people have wildly different ideas about what should that encoded instruction look like. And we'll have some specific thoughts. There's this great scene in one of the old Pink Panther movies where the meanie drags the young heroine into the back room, and then all of a sudden you hear her scream, "Ah!" And so the Pink Panther runs back, all gallantry, of course, and you discover that what the guy has done, he's lashed her to a chair and he's pulled on this big metal glove with long claws and is standing like this next to a blackboard, waiting for it to squeak. So, obviously pure torture, at least to the Pink Panther's mind. Sorry about that. Okay, so what is it we need to specify, right? Well, there's a sort of notion of we want to be able to specify. Ooh, I can see my claw marks right there. We want to specify an operation, and the operation almost certainly needs some operands. And usually there's a destination involved where to put the result. And so we would expect whatever we're going to do to involve some way of taking our instruction word, our binary encoding of the instruction, and have it specify everything that we need to do in order to make our little data path do its thing. And some data paths are complicated. They have lots of places to get information from in terms of operands. Some only fetch information from the scratch pad registers. Other instruction sets allow you to take one of the operands from memory. So you could, it involves actually loading some information from memory, which means you have to compute an address. People have been all over the map depending on how complicated things are. How the instructions are encoded can be quite different. Some people use a Huffman-like code, where they actually have a string of bytes, and it's a variable length code, which means that some instructions are encoded in a single byte, and other instructions take 8 or 9 bytes to encode. A simpler approach, which is the one we're going to be taking, is we're going to have all the instructions be exactly 32 bits long, and we'll choose to have just, I think, as it turns out, just 2 formats of instructions, and as you'll see that evolve in just a second. Okay. The question is, how do we decide what's right and what's wrong? And there's no right answer to that question, or no correct answer. But what we're going to do is a sort of a mix of sort of engineering tuition. What operations do you think we need our machine to be able to do? And then a little bit of sort of art and polling, if you want to think of it that way, where we're going to be running a lot of benchmarks to figure out whether the proposed feature we want to add to our instruction set actually accomplishes anything. Or, our programs run faster? Are they shorter? Or what would be the advantage of adding those extra transistors to our CPU design? Will we get something for it? Will the investment have the right amount of return? And what people have gone to, and I'll put my cursor here on top of this RISC philosophy, reduced instruction set computer. For a long time, computers have got more and more complicated. And a really complicated instruction set that provided for a huge a repertoire of where you can get information from to operate, and lots of destinations and a zillion operations, not just simple add and subtract, but polynomial evaluate and FFT and so forth. How far do you go? And for many decades the answer was, well, the sky's the limit. More complicated was better. That showed you had a more sophisticated computer. And then when we got into the integrated circuit era, in which there was a real value to things being compact and ultimately not very power hungry, we got into this sort of mode of saying, well, what's sort of a minimum set of things we can do? And in fact, if I have a simple instruction set, maybe I can actually build a machine where the clock rate is much faster. That's, instead of stuck at 100,000 operations a second, it might be able to do 1 billion simple operations per second. And it might be able to do 1,000 small operations in the same time it took you to do one complicated one might turn out to be a better way of thinking about the problem. And in fact, that sort of turned out to be the case. So for a long time, the core execution engine inside the laptops is very much one of these RISC computers, reduced instruction set computers. And then, at least in the case of Intel processors, there's a sort of this separate front end that takes the more complicated encoding of the x86 instruction set and translates that into a sequence of these RISC operations. So we're going to build a RISC computer. And it actually, you'll discover it performs pretty well.